So thanks a lot for having me. My name is Alexei. I'm a final year PhD student at the Imperial College in London, and co-founded Interlay a year ago. Interlay is an R&D company that focuses on research and development of cross-chain infrastructure. I guess we're best known for the Trustless Bitcoin Polkadot bridge, and um, a lot of the work that we're actually doing in practice is based on the research that I'm presenting today. So today I'm going to talk about cross-chain communication, provide an overview, detail different properties and aspects that are relevant in today's research and practice. Then I will talk about the impossibility result that we have derived in our last year's research. This is in collaboration also with Dionysus. And finally, I'll talk about Xclaim, which is an approach towards financially trustless cross-chain communication. So somewhat circumventing, we're trying to mitigate this impossibility result in practice by using incentives. So the concept that makes most cryptocurrencies work in practice. So the talk today is based on two research papers. On one hand, Xclaim, which is accepted at IEEE S&P in 2019, and our joint work with a few other researchers from different institutions on basically a systematization of knowledge on cross-chain communication. So interoperability, I think we can most of us can agree, is a quite relevant topic nowadays, with over 5,000 different cryptocurrencies existing, most of them differing in design and purpose. And with adoption of cryptocurrencies basically growing, we need to figure out a way, or we need to think about a way of how we can communicate across different systems without maybe requiring a trusted third party, or at least without relying on too many assumptions on top of what we have in the existing blockchains. Now, cross-chain communication in general as a research problem can be traced back to the non-blocking atomic commits in distributed databases. There you would want to synchronize multiple databases and transfer data from one to the other. Now, the big difference that we will see between these two problems is that in distributed databases, you would typically assume crash failures. You wouldn't assume that the administrator of the databases is malicious and tries to corrupt the data. Whereas in distributed ledgers, you must assume that Byzantine failures are possible, that one or both ledgers that you're communicating with can be corrupted, and in the worst case, your protocol as well may be attacked by participants. Now, if we look at the protocols and general use cases in practice today, we can identify four main scenarios in which cross-chain communication is relevant. The first and probably most well-known are cross-ledger transfers and exchanges, meaning atomic cross-chain swaps or cryptocurrency-backed assets, such as Bitcoin on Ethereum, or essentially matching different trades on different blockchains. However, we also see concepts or essentially the same protocols for cross-chain communication when we synchronize different shards in sharded environments. And essentially here, each shard is often a blockchain of its own, so the protocols and properties are often the same or very similar, yet sometimes with a slightly more homogeneous security model. The first cross-chain communication protocol to be deployed in practice, however, was actually merged mining. Merged mining allows one blockchain to create blocks essentially to bootstrap on top of the proof of work of another blockchain. And this was the case for Namecoin and Bitcoin, where Namecoin would allow Bitcoin's proof of work solutions to generate new Bitcoin Namecoin blocks. So Namecoin would actually verify Bitcoin's proof of work and then automatically spawn the Namecoin block using this merge mining technique. And this is essentially the first kind of cross-chain communication example in practice. And finally, something that I guess most of us are familiar with, sidechains. Sidechains are often used as an umbrella term for cross-chain communication. We try to kind of position the term sidechains into extension of functionality of one parent blockchain. So for example, if you peg a system to Bitcoin, where your system relies either on the security of Bitcoin or uses, for example, the same currency, then we consider this as being a sidechain. So when we talk about cross-chain communication, we will typically assume that there are two distributed ledgers with a consensus committee each. Now, we use the term consensus committee as an abstraction. We know that Bitcoin and Ethereum actually use random lead election protocol to select one leader per round. However, we basically use this as abstraction because at any point in time, you have a snapshot of all consensus participants. So in a cross-chain communication protocol, you will have two parties or processes. We'll call them Alice and Bob. We'll assume Alice is mainly operating on Bitcoin, whereas Bob is mainly operating on Ethereum. Now, Alice owns transaction TX1, the blue one, and Bob owns transaction TX2. Now, when I say owns, I mean that Alice can broadcast transaction TX1 by signing it, and Bob can do the same thing for TX2. Now, TX1 is a valid Bitcoin transaction, and TX2 in red is a valid Ethereum transaction. Now, let's assume that Alice, for some reason, really wants transaction TX2 to be included in Ethereum. So she knows exactly what the description of TX2 is, and she also knows that TX2 is a valid Ethereum transaction. And the same goes for Bob. Bob, for some reason, wants transaction TX1 to be included in Bitcoin, and he also knows the properties of that transaction and that it is indeed a valid Bitcoin transaction. Now, this may sound a bit abstract. Let's use a practical example here. Let's assume that TX1 gives Bitcoin to Bob, so it basically spends from Alice's UTXOs and creates a UTXO spendable by Bob, and TX2 on Ethereum assigns a value of ETH, an amount of ETH to Alice's account. And this already kind of is a first hint towards how we derive the possibility result later. Now, the goal of cross-chain communication is to synchronize the inclusion of these two transactions in both blockchains. Now, if we jump to theory, we then will see, or essentially we introduce in our paper, 3 properties for cross-chain communication: effectiveness, atomicity, and timeliness. Now, those of you familiar with the fair exchange problem will probably already see that these properties resemble that of a fair exchange. Now, effectiveness basically states that if Alice and Bob are honest and they want to execute this exchange or this cross-chain communication protocol, and both transactions are as expected by both Alice and Bob, meaning they're also valid, then transaction TX1 will be written to Bitcoin, transaction TX2 will be written to Ethereum. However, if one of the two transactions is not as expected, so not valid or does not meet the properties specified by the cross-chain communication protocol, or Alice or Bob don't want to proceed with the protocol as well, then the protocol will abort. Next, atomicity restricts the possible outcomes to those where Alice and Bob basically face no damage, are not left at a disadvantage. This means that TX1 and TX2 are either both included in the respective blockchains or none of them are. And finally, timeliness is a liveness property which states that Alice and Bob will eventually write TX1 and TX2 to the respective blockchains if they're honest and want to proceed with the protocol. So in our research, we studied a lot of existing cross-chain communication protocols, and even though there's a lot of different kind of use cases and goals and approaches, it appears that they all follow the same generic few steps. The first one being a setup phase. In the setup phase, you will agree on the 2 blockchains that are involved. You will agree on the transactions that are to be included in both blockchains and how these should look like. So, for example, you would agree on how much assets are being transferred by each transaction, to whom, and under what conditions. Then when we initiate the cross-chain communication protocol, the first step kind of in this case is to make a commitment on a blockchain X. Now, blockchain X in our example will be Bitcoin. So we'll make a commitment on the Bitcoin blockchain that is publicly verifiable. This can be, for example, in the form of broadcasting a Bitcoin transaction that can be then verified by the counterparty. Now, the second step is to verify this commitment on the other blockchain by the counterparty or somebody else who is assigned to do this task. And then if this commitment on X is indeed as the protocol dictates, then execute a commitment on blockchain Y, or in our example, Ethereum. Now, if the commitment on blockchain X is not valid, then you abort the protocol. And optionally, some protocols also introduce an abort phase on blockchain X. And this is basically a difference between two assumptions, which I will talk about in more detail later. Important to note here that, of course, we assume that both blockchains have persistence and liveness, meaning that essentially we make use of the persistence parameter K and the liveness parameter U on both blockchains to basically determine when we can be sure that a specific commitment is indeed included in the blockchain, is essentially stable. So one of the questions that we then asked ourselves was, can we actually achieve cross-chain communication without a trusted third party? And in my PhD, my goal was to figure out a way how to synchronize to blockchains without a centralized third party, but we realized that this is actually not really possible. Now, let's get back to the previous example that we used with Alice and Bob. So recall we said that Alice and Bob want to synchronize the inclusion of transactions TX1 and TX2, and basically we model this as an exchange of assets. So TX1 gives BTC to Bob and TX2 gives ETH to Alice. So what then happens is that this cross-chain communication protocol, which would synchronize the inclusion of TX1 and TX2, it becomes a fair exchange protocol as well, because it will essentially, if successful, achieve a fair exchange of Bitcoin and Ethereum between Alice and Bob. Now, we know, however, that fair exchange is impossible without a trusted third party. And there's numerous papers that derive this result, one of them being by Pagnier and Gärtner in 1999. So what we do in our work is we provide a reduction, or we suggest how a reduction would look like from the cross-chain communication protocol to fair exchange. And then we derive the result that there exists no cross-chain communication protocol tolerant against misbehaving nodes without a trusted third party. Because if there were such a cross-chain communication protocol, there would also be a fair exchange protocol, which is known to be impossible. Now, I won't go into the theoretical details. I do recommend the interested reader to take a look at our paper. What I will instead try to do is provide an intuition of how this actually reflects in practice. Now, again, looking at our model of Alice and Bob, let's make this a bit more interesting by introducing a smart contract on Ethereum. So now we basically force Bob to broadcast or to include transaction TX2 in Ethereum if Alice behaves correctly and initiates the cross-chain communication protocol. So in practice, this would be a smart contract that basically transfers ETH from Bob's to Alice's account if Alice can prove that she made the Bitcoin transaction. So when the protocol initiates, Bob has committed, Alice will then commit as well. And we know that Bob has no choice but to basically release his assets to Alice if she behaves correctly. The big question here, however, is how does the smart contract on Ethereum become aware of TX1 being included in Bitcoin? And we basically need to make one of two assumptions to always ensure that this protocol executes correctly if Alice is honest. The first option is that we assume synchrony and availability, meaning that Alice, or this can also be Bob, is online and will submit a proof of TX1 being included in Bitcoin to the smart contract. And this message sent by Alice to the smart contract on Ethereum is delivered within a known bounded delay. Alternatively, if we cannot assume that we have a synchronous model and that Alice will be available and this message will be delivered on time, then we must assume a trusted third party. And the term trusted third party here is often confused with the term because of the word trusted, as it is used in cryptocurrencies and distributed ledgers. But from distributed systems perspective, a trusted third party must be then selected, and this trusted third party is online and honest. So it will either inform the smart contract that Alice made this Bitcoin payment, or it just directly replaces the smart contract altogether and will force Bob to release Ether to Alice if she transfers BTC to Bob on Bitcoin. Now, following the impossibility result by Pagnier and Gertner and other discussions, we conjecture that the synchrony assumption and a trusted third party are actually equivalent. And the intuition behind this is that in a synchronous model where Alice is honest, in this case to herself, but it can be also Bob who is honest to Alice, and online, then Alice becomes her own trusted third party, or Bob becomes a trusted third party. So you need to agree upfront in a protocol who will make sure that the communication is in fact successful. And this again is essentially equivalent to agreeing on a trusted third party. The main question, hence, when designing and building a cross-chain communication protocol is to agree and decide which trusted third party we want to use. Now, in a cross-chain communication protocol between Alice and Bob, we can agree that this trusted third party is either Alice or Bob, the consensus committee of Bitcoin, for example, or the consensus committee of Ethereum. And a practical example here would be the Liquid sidechain, where the consensus committee of the Liquid sidechain maintains the peg from Bitcoin to Liquid. Or the trusted third party can be an external committee or a single trusted third party. So you can revert to having a centralized exchange, transfer your assets, or you can try to have a committee or other models. And this is where the cross-chain design framework that we present and put together in our SOK paper comes to play. What we did is we mapped out the different models that you can choose at each step of a cross-chain communication protocol. And you often can combine those. It's not always meaningful and does not always yield a practical result. But in theory, you can basically plug and play between different trust models at each step of a cross-chain communication protocol. Now, in consideration of time, I won't go into too much detail here. And if we have time at the end of the talk, we can come back and discuss different models, different combinations. And also we can chat about our analysis of the existing cross-chain communication landscape. Now, one important thing to mention here is that in general, there exist two types of cross-chain communication protocols that can be essentially grouping them by use case. On one hand, you have exchange protocols. And this is quite straightforward. These are protocols that attempt to achieve an atomic swap or a change of assets or exchange of information onto different blockchains. So here, you will basically synchronize the inclusion of two transactions on blockchain X and blockchain Y. And in this case, you will typically implement a two-phase commit protocol with a dedicated abort step. So Alice will commit, Bob will commit, they will verify each other's commitments, and then both will either commit or abort. They both will either execute the exchange or they will abort the exchange. And this, for example, is the case for HTLC atomic swaps. This does typically require some form of off-chain communication, especially if you want to have a way to unlock your assets or abort the exchange, especially when operating between Bitcoin, for example, and Ethereum. Now, the other protocol family are asset migration protocols. And as the name states, the goal of an asset migration protocol is to move one asset or one object from one ledger or blockchain to another. And you typically would do this by applying concepts from concurrency. Specifically, we will obtain a write lock on this object or asset X on blockchain X, and then create a representation of this asset or object on blockchain Y. We will then apply the updates to the state of this asset on this other blockchain. For example, the simplest being a change of ownership. And then when we go back, when we want to basically propagate these updates back to the original blockchain, we do that. And the simplest practical example here are wrapped assets. So for example, wrapped Bitcoin on Ethereum, where you will then also always ideally, if the protocol works correctly, propagate the changes of ownership of these Bitcoin-backed assets back to Bitcoin when you redeem these Bitcoin-backed assets for actual Bitcoin. And this is essentially what Xclaim tries to achieve. Now, we call Xclaim and Trust basically a protocol that works towards financially trustless cross-chain communication. And I'll explain in a second why we coined this term. Now, Exclaim makes use of cryptocurrency-backed assets and basically introduced kind of a slightly more formal approach to this. And the idea of a cryptocurrency-backed assets is to create a one-to-one backed token on another blockchain that is backed by locked assets on a backing blockchain. So using now Bitcoin and Polkadot here as example, because that's where we're also actually implementing Exclaim. When you issue Polka BTC, which we shall call this Bitcoin-backed asset on Polkadot, you first lock Bitcoin on the Bitcoin blockchain and then create or mint a Polka BTC unit. Now in Exclaim, we use something called vaults to ensure that Bitcoins are locked on the Bitcoin blockchain. And I'll come to that in a minute. Now, these wrapped assets, Polka BTC, you can use just like any native currency on the issuing blockchain, so on Polkadot. You can use them in decentralized exchanges, in stable coins, payment channels, lending protocols, essentially anything you want. And then whoever receives these Polka BTC tokens at the end or whenever can then go back to Bitcoin and redeem Polka BTC for actual Bitcoin by destroying these backed assets. Now, Exclaim was built such that it works essentially with any backing blockchain. So the protocol makes absolutely no assumptions about the functionality of the backing blockchain. We do assume some form of smart contracts on the issuing blockchain. And again, I will provide a more detailed discussion in a second. Now, one of the main challenges when trying to get this work for Bitcoin is that we essentially want to achieve two things when creating cryptocurrency-backed assets. We want to lock Bitcoin and mint Polka BTC atomically. So we only want to create Polka BTC. There's actually Bitcoin locked on the Bitcoin blockchain. And we can indeed achieve this because we can verify the state of Bitcoin on Polkadot by implementing a cross-chain SPV client. Vice versa, however, this does not work because Bitcoin does not support sufficient functionality to verify external events or events that occur on other blockchains. So the question is, how do we ensure that we unlock the Bitcoin that are locked basically when a user wants to redeem Polka BTC? Now, the first intuition for a lot of things on Bitcoin is to use HTLCs because these often work as a golden hammer and can be applied to a lot of different protocols. Unfortunately, they do not work in this scenario. And the reason is that in Bitcoin's UTXO model, we have to know upfront who will be the redeemer of these coins, so who will be taking the coins out of this lock. However, since we can change the ownership of wrapped assets on the target blockchain, on the issuing blockchain, it is impossible for us to predict the recipient and the person who will be redeeming Bitcoin at the end of this process. And in addition, it's not possible, at least to this date, to generate and store secrets in a publicly verifiable manner on a public blockchain, which makes this even more complicated. So I've actually seen protocols that try to achieve this self-custody. So basically trying to mirror or this bridge, this cryptocurrency-backed asset construction using HTLCs. But what you end up doing is broadcasting an update to Bitcoin for each transfer that you execute on the other blockchain, which kind of defeats the purpose of moving assets to another system because you still end up broadcasting transactions then on both chains. So to kind of find a meaningful solution, we need to introduce some form of intermediary to hold Bitcoin locked while Polka BTC exists. And this is where vaults come into play. Vaults are essentially users on Bitcoin and or Polkadot that hold Bitcoin locked while Polka BTC exists. Now, essentially, this means that vaults receive custody, at least in the current design, over users' Bitcoin. Now, of course, we must somehow enforce correct behavior of these vaults and prevent them from simply running away with the BTC they have in custody. So what we do is we require them to lock up collateral, in this case on Polkadot, and then we basically require these vaults to proactively prove to the target system, to essentially the cross-chain light client deployed on Polkadot, that they indeed executed Bitcoin transactions as the protocol dictates. So most importantly, that vaults released the BTC to the users that are redeeming Polka BTC for Bitcoin. The interesting part here is that anyone can become a vault. So there are actually no restrictions. There is no registration process. You don't need to ask for permission. So it's a permissionless system, which also means that you can be your own vault. You can essentially run your own vault client if you don't want to trust somebody else. You will still have to lock up collateral as protection to other users. When you transfer BTC to somebody else, you need to convince them that you will not steal these Bitcoin the moment that you transfer Polka BTC to the other user. So to summarize, we have 3 requirements for a user to become a vault. You need a Bitcoin wallet, you need a Polkadot wallet, and you need to lock up collateral on, in this case, Polkadot. Now, if you look at the general system model, we see we have different kind of types of users, but these are mostly just grouped by use case. And then we have vaults, as mentioned, so a dynamic and permissionless set of intermediaries that we do not trust because we collateralize them and enforce proactive verification through a cross-chain SPV client. And in addition, we have a smart contract or some form of consensus enforced execution environment that is deployed or hosted on the issuing blockchain. So in our case, on Polkadot, and enforces and checks correct behavior of vaults. And then if vaults misbehave, slashes their collateral. Now, let's take a quick look at the XLM architecture. While the design was purposefully kept as simple as possible, beneath the hood, there are quite a few moving components. We have basically protocols for issue, redeem. We have a protocol to replace vaults if they want to leave the system. We have a component to essentially maintain the balances of Polka BTC. We have a registry that keeps track of vaults, and then a collateral module that keeps track of the collateralization of vaults. Meaning that this collateral module connects to an exchange at Oracle that receives information about the current BTC to, let's say, Polkadot exchange rate, and then ensures that the collateralization rate is secure. Now, why do we need to think about this? The problem here is that vaults need to lock up collateral to secure the BTC. However, if their collateral suddenly devalues, then vaults have no incentive to behave correctly anymore, assuming that they're short-term economically rational. And then vaults would actually be incentivized to steal BTC. So we need to ensure that we have some system in place to maintain the collateralization rate. Another important component is the chain relay. And I'll skip over this because I think most of you already know how this works. But on a high level, a chain relay allows us to track the Bitcoin main chain, verifies the difficulty adjustment, the proof of work, verifies that indeed we have a chain so blocks basically have the correct ancestor. And then it also is able to detect the Bitcoin main chain. So when given 2 or more different chains, the SPV client or the chain relay will be able to detect the one that has the most accumulated proof of work. And then we can use this chain relay to verify that specific transactions have been included in Bitcoin. And then we also implement some partial validation for these transactions to actually check that the value of the transaction and the recipient, for example, are as we expect. So let's take a brief look at XClaim protocols. The issue protocol is a 3-step process. In the first step, the vault registers with what we call the BTC parachain, which is essentially this Bitcoin bridge component on Polkadot. So the vault registers by locking up dot collateral. The collateral can be locked up essentially in any currency. Ideally, it's some form of stablecoin to avoid or to reduce fluctuations. Here we use dot currency as example. In the second step, the user transfers BTC to the vault. Now, one thing to mention here is that this is actually a 2-phase commit protocol, because first the user requests to issue Polka BTC, reserving some amount of the vault's collateral, and then only makes the Bitcoin transfer. And this is necessary to prevent race conditions. So the vault trying to take out collateral before the user is able to finalize the minting process, or multiple users trying to use the same collateral as security for their locked Bitcoin. And then in the third step, the user submits a proof to the BTC relay client on the Polkadot, showing that the user has now transfer BTC to the vault, and then the system will mint Polka BTC to the user. Now, in practice, the user can do this manually, or what we actually have built on Polkadot is we have a client built into the user interface, into the web-based user interface. So your browser will fetch the proofs on your behalf if you want to do that and submit a transaction to the Polkadot BTC parachain. So kind of it's a model where users can choose between usability and security, depending on what they want and how technically versatile they are. Now, to redeem Polka BTC for Bitcoin, it's again a three-step process. At first, the user locks Polka BTC in the BTC parachain. Essentially, we can also consider this being a burn because these tokens will then, at the end of the process, be destroyed. In the second step, a vault is selected, and then this can be either by selection of the user or some random sampling or another mechanism. So in Polka BTC, for example, we have a reputation-based system that incentivizes vaults to behave correctly and to maintain essentially high availability. And this way they can earn more fees because they're selected more often for redeem requests. Now the vault will then transfer BTC to the user and finally submit a proof again to BTC Relay showing that it adhered to protocol rules, that it released BTC correctly to the user. And only then will the vault's collateral be unlocked, and the vault can choose whether to keep it in the system and allow more or new users to issue Polka BTC or to take it out. Now, as mentioned, exchange rate fluctuations are indeed a problem. And I believe we've seen this in practice, also in other bridge constructions that are similar to Exclaim, that sudden changes in the exchange rate between Bitcoin and the collateral currency may lead to problems. Now, what we do in Exclaim, we have a multi-step process to try to mitigate this should something go wrong. We use currently a 200% over-collateralization rate. This can be essentially lowered as well, depending on the stability of the exchange rate. But to be more on the more secure side, we start with a 200% over-collateralization rate. Now, up until 150%, we consider that everything is still fine. There's still sufficient buffer for vaults to be incentivized to behave correctly. Now, below 150%, we will instruct vaults to actually add more collateral to the system or to either execute a redeem request with themselves. So if a vault holds Polka BTC, they will be asked to redeem these Polka BTC to rebalance the system. Or essentially what we also do is we allow users to redeem BTC at a better rate. So if a user during this phase executes a redeem request, the user will get his Bitcoin back and earn a small premium in Polkadot currency or the collateral currency because he contributed to rebalancing the system. Next, if this does not help, if basically we're still in an imbalance, then we start an auction protocol where under-collateralized vaults can be replaced by other users. And this is similar to MakerDAO's Keeper protocol. You can basically kick out a vault and replace it by providing collateral. And you will do that if you think that you can earn sufficient fees on this bridge in the future and that you expect that the exchange rate will go rebalance again. And for you, essentially the change in exchange rate may not be as critical because you consider the current spot price and not what it was, let's say, a month ago. And finally, if nothing else helps, we will trigger automatic liquidation. So essentially all vaults are then instructed to return BTC to users. And if they do not do that, their collateral is slashed and users are reimbursed. So of course, we never really want to get to this liquidation step because this does mean that we have some problems with smart contracts that use or other applications that use Polka BTC. And this is something that we in practice, of course, need to take into account. But in the majority of cases can avoid by having these different steps and phases before getting to liquidation and adding other auction or exchange protocols on top of that. So what we're going to include in Polka BTC is an auction protocol where you can basically trade Polka BTC against collateral to rebalance the system on the more essentially like an exchange, but for users who hold Polka BTC. Now, briefly on the system requirements. So on the backend blockchain, we don't really have any requirements for Bitcoin. You just need to be able to make simple transfers and that's it. And this makes Xclaims essentially compatible with almost any blockchain that exists today. On the issuing chain, we need some form of smart contracts. Specifically, we need a cross-chain SPV client, a chain relay that allows us to verify the state of the backing blockchain and to check that specific transactions are indeed included. We need some form of on-chain assets or tokens, like colored coins or tokens that we can use to represent the wrapped assets. And we need some form of conditional payments specifically to ensure that we can implement collateralization and slashing. And this makes Xclaim compatible with Ethereum, Polkadot, and most other smart contract capable blockchains. Now, in practice, if you basically have smart contracts on the backend blockchain, you do not need this complex or this mechanism of collateralization and vaults, but instead you can use smart contracts on both blockchains. And this has been described in a few other papers. In this case, Xclaim can be seen as a performance improvement in case smart contract synchronization is costly or complex to implement. Now, finally, when we first wrote this paper in 2018, we compared Xclaim to atomic swaps. This is basically a very small example to showcase the differences that you will have across different blockchains that you connect. So, for example, we looked at atomic swaps between Bitcoin and Ethereum if implemented with HTLCs, and then we looked at how atomic swaps would perform if we first create a wrapped asset on Ethereum in this case, but that holds the same for Polkadot, and then execute these atomic swaps without having to synchronize two chains for each exchange. And then we saw that if you use wrapped assets like with Xclaim, you will be 95% faster and around 65% cheaper, although the costs, of course, may vary and are probably slightly different to what they were back then. Now, finally, to conclude this talk, some teasers about ongoing work and future research. One of the main problems that we have with Xclaim, and I think generally decentralized bridges in the current blockchain space, is collateralization. While this collateral ensures that vaults or intermediaries have no incentive to misbehave and is kind of beneficial for users, it does mean that it's a big capital investment for vaults to become a vault, essentially, because you need to not only, so on one hand, you need to lock up collateral, and then if you as a vault yourself want to mint Polka BTC, you need to lock up Bitcoin and the collateral amount, which is quite a lot of capital, and it will range between 200 and 300% of what you actually would do if you, for example, go through a centralized exchange. Now, what we've been working on in practice is to basically apply some form of commit chain architecture to Xclaim, and basically combining principles from payment channels, commit chains and rollups, and the current Xclaim design to prevent theft cryptographically, at least over specific periods of time. This is currently in draft form, and we most likely will release an extension to the current Xclaim protocol within the next 3 to 4 weeks that allows us to significantly reduce the collateralization of vaults. Other work that's been going on in parallel is synchronization of clocks across different blockchains. Right now, we typically have to revert to absolute time locks, so assume some global clock, some global notion of time, which we know might be quite tricky because the block generation rates of two different systems are not synchronized. They can be different, they can deviate. So we've been working on a mechanism to create relative time locks across blockchains. And finally, an interesting avenue for future research is to enable collateral lockup directly on Bitcoin, so that at least you don't have to worry about exchange rate fluctuations, but can at least lock, essentially, if collateral is needed, you can lock it up directly on the backing blockchain. So you could use Bitcoin to back Bitcoin-backed assets. This still would mean that we have some capital inefficiencies, but you would avoid over-collateralization because you don't need to compare the value of two different assets. And that's it from my side. Thanks a lot for the attention. As mentioned, this talk is based on 2 research papers, which are linked here. And yeah, I'm happy to take any questions.
Well, thank you very much, Alexei, for the talk. I think there might be several questions from the audience, but let me start with one. So one of my questions is regarding the use of the trusted third-party terminology in the first part of this talk regarding the SOK. And I think a lot of the crypto community is using this term to mean an external party that is trusted to behave honestly. And they would categorize Bitcoin or Ethereum as a system that does not involve a trusted third party. For example, the community of Bitcoin maintainers or the community of Ethereum maintainers, the miners, they would not consider them a trusted third party because they stem out of an assumption on honest majority. So can you comment on that? Like, is your definition somewhat different here in this paper? And how does it relate to the definition of a trusted third party in the literature of distributed systems?
That's a very good question. And I think this is also one of the points that we've discussed a lot with the community and a question that we actually often get when talking about this result. So in the paper, I've actually updated this to make this more clear. The definition that has been adopted in cryptocurrencies and blockchain for a trusted third party is somewhat different, because we typically, when we say something is trusted, we imply that this party has custody over our funds, can steal and misbehave, it can essentially break the entire protocol. Now, this is actually also the case in cross-chain communication, and this is also kind of the same definition that we use in our kind of definition. Now, the difference here, of course, is, and there is, of course, a difference between using a single party, a single intermediary, or having a huge committee, or essentially a distributed system of basically that uses a permissionless set of participants like Bitcoin or Ethereum. However, if you abstract this, you still basically have a trusted third party. You still trust that this entire system will behave as the protocol dictates. Now, so what we try to also make more clear in the paper, and then also refer more to an honest online party, is that it does not matter what implementation you have. If you rely on some form of online third party that basically will execute the cross-chain communication protocol or enforce its execution correctly, then that is a trusted third party in the sense of distributed systems.
Thank you. Any other questions?
Hello, thank you, Alexei, for the talk. I was wondering what's your opinion on privacy of these asset migration protocols that you have been presenting in the presentation. There have been several works looking at the privacy of atomic exchanges, where we are trying to come up with protocols that hide which tokens are being exchanged and who pays to whom. What is your opinion? What do you think? If those privacy goals also carry over to these asset migration protocols, or there are any other privacy goals that you have in mind and would be interesting to have as well?
Thanks. And that's also actually a very interesting question to discuss. In general, cross-chain, like when you connect to different blockchains, this does have a rather negative impact on privacy, because it allows us to access a new source of information to, for example, link payments and link addresses. In fact, when we first studied merge mining, we used merge mining to attribute miner payout addresses that were previously unknown through information that we had on Namecoin. Now, with exchange protocols, there's quite a bit of work that's being done to hide, basically, or to essentially prevent third parties from being able to trace which two parties actually are exchanging assets. And typically, you try to prevent these two transactions on two different blockchains being linked to one another. And in Hashlocks, you would try, for example, to do that by making sure that at least the hashes are different, or maybe split up the payment across different transactions. Now, in asset migration protocols, you could do something similar. The difference here is that you need public verifiability. You need to publicly verify that assets are indeed locked on, like, say, Bitcoin, when you create wrapped assets on Ethereum. So this makes things a bit more tricky, because it's not a one-time thing, but it's a permanent, like this lock has, this consistency has to be maintained over a longer period of time. As of this moment, I'm not aware of protocols or approaches that allow us to hide which assets are actually locked up and migrated. In fact, on the contrary, we really want to know if the Bitcoin is still there and if it's locked. Now, there may be ways to kind of hide the redeem transaction and to kind of prevent a third party from checking who is actually redeeming Polka BTC, let's say, for Bitcoin, and to link those two addresses. But that's, I think, the most we can currently do. In the future, one interesting avenue for research would be to apply zero-knowledge proofs and mechanisms to prove that Bitcoin are locked on Bitcoin using a zero-knowledge proof, and then vice versa, basically handle the unlocking in a similar manner. This is a bit complicated because of, for example, on Bitcoin, we have some limitations with the primitives and compatibility with, for example, snarks. But I do see this kind of as a potential to ensure privacy and potentially also to leverage the compression properties of zero-knowledge proofs for better performance.
Okay, any more questions?
Hi, may I ask something? This is Aris. Yes,
Sure, please go ahead, yeah.
Yeah, I just know if you hear me. So nice to meet you. My name is Aris Pagourtzis. Thanks for the nice talk. And I want to ask about a little bit about the impossibility result. So this is the need for trusted third party is connected to synchrony, to I mean, okay, the impossibility holds for asynchronous systems, right? If I understood it correctly. So can't we, in real systems, can't we assume some form of synchrony anyway?
So yes, I mean, in practice, this result does not prevent you from building a protocol in practice. Just that the guarantees that you have depend on your synchrony assumptions. So like HTLC atomic swaps or atomic swaps that use SPV proofs, where you will prove to a smart contract that you made the Bitcoin payment, or your counterparty will spend from your lock using the same secret that you used to spend from their lock. Such protocols basically don't have a dedicated trusted third party. You only have the two involved parties, let's say Alice and Bob. Now, they work in practice, but the problem is if Alice, for example, crashes or her message is not delivered to the smart contract, for example, the protocol may fail. And the reason is that you must make one or two assumptions here. Either you allow the assets of both participants to be locked up indefinitely, and then Alice and or Bob have an infinite amount of time to finalize the process. But this again means that, if one of the parties remains offline, that the counterparty faces financial damage because the assets will be locked up indefinitely. Or you have to introduce some form of a board step, so a time lock, for example, that allows Bob to take out his coins if Alice does not proceed with the protocol. Now, in the former case, if Alice does not manage to then broadcast her proof to, let's say, the smart contract, or to spend from Bob's lock on the other blockchain using, let's say, a hash lock, then Bob, after the time lock expires, can take out his coins. And in the worst case, Bob will have received Alice's coins already on the other blockchain and now basically recovers his own funds, and he steals from Alice. And then in this case, you have to assume either that Alice will make them broadcast, she will manage to deliver the message, or Bob is honest and will not take out his coins and wait until Alice comes online. And again, you trust Bob to do that. Or Bob makes sure he transfers coins to Alice, or he aborts the entire protocol. So in practice, there are ways to mitigate this, but you always have to make some form of assumption. And that's essentially all that the result states. You can still build these protocols. You just have to be aware of the requirements you have to ensure security.
Okay, fine, great, thank you very much.
Okay, any additional questions? In case there's no further questions, I think, Alexei, you had this nice matrix where you compared some things that you promised to go back to. And since we have a little bit of time, maybe we can devote it to that.
Sure, let's do that. That sounds great. So essentially, we have these two tables that kind of are the output of our cross-chain design framework. And I think what might be quite interesting is to talk about a specific example of protocols that are currently implemented in practice and have gained quite a bit of traction, namely wrapped assets. So we know that there's a lot of wrapped Bitcoin that exists on Ethereum, and there are actually different models and different constructions that allow us to do essentially bring Bitcoin to another blockchain. So the simplest one being a centralized exchange, right? So I don't know, can you see my mouse? Let me see if I can use a pointer. That should work, right? Excellent. So essentially custodial wrapped assets, and an example here for is WBTC. Essentially here you assume that you have a trusted third party, right? So we have this kind of black dot that says, okay, we assume a trusted third party. Now, this trusted third party is not dynamic because in the case of WBTC, we know exactly who this is. This is BitGo. It's a custodian. It's determined upfront, and other people cannot become this custodian. You cannot choose to be your own trusted third party here. You cannot become one of these custodians easily. You need to ask for permission. Now, WBTC does not use collateral to secure your assets. So if BitGo fails, or the assets are seized, or it steals your coins, there is nothing to reimburse you. So you trust that BitGo will be able to maintain the security of your funds, that it will have them securely locked, and that BitGo will not misbehave, which is a fair assumption in practice. And we see that a lot of people make this assumption and trust BitGo as a custodian, which is a fair thing to do in practice. Now here we say that the type of TTP or trusted third party is essentially an external custodian. So EC, meaning external custodian. So it's an external party that is not directly involved in a consensus of either Bitcoin's or Ethereum's consensus, and it's a single and restricted third party. On the verification step, again, the verification is performed by BitGo itself, and basically we call this an external validator. So again, the validation happens by confirmation of BitGo or some other custodian, and basically they tell the smart contract on Ethereum that yes, the assets are locked up correctly. There's actually been an interesting announcement recently with WBTC stating that WBTC and Chainlink will cooperate to implement a proof of reserves, where then Chainlink oracles or Chainlink validators will check that the assets are indeed locked on Bitcoin. This would still fall into this category of external validator, but because again, we have an external committee, external group of people who check that the assets are locked up correctly and then just submit a signature to the smart contract. It does improve robustness because now you have at least, if Bitcoin misbehaves, we can assume, or the assumption is that these other parties, Chainlink validators, are not directly colluding with BitGo. At least the probability is not as high. Now, I will skip over RenVM because at this point, there is not much technical documentation available. At the moment, as far as I know, RenVM actually represents a custodial wrapped asset model to some extent because the secure MPC protocol is not yet deployed. So I think as far as I know, and there was an article by, I think, OneChain that discusses this, that it seems that the assets held locked by Ren are all on one single AWS instance and basically held in a multi-sig. So it's, we don't know who exactly is part of this multi-sig, so we must assume that it's similar to being a centralized third party. In the future, Ren wants to adopt a similar model to TBTC, so I'll talk a bit in more detail about TBTC instead. So TBTC essentially, again, makes use of a trusted third party. In this case, the trusted third party is a committee. So currently this committee is not dynamic, but according to the TBTC website, it's a group of about 80 different participants. So early investors into the Keep token and a few other trusted parties that are basically responsible for holding users' assets in lock. Now, TBTC uses collateral to secure users' assets. So these signatories lock up collateral on Ethereum, and if they misbehave, if they steal BTC, the user will be reimbursed. Now, maybe one point to mention about the committee. So the committee is an external custodian because, again, the committee is not party to Ethereum's or Bitcoin's consensus, or at least there's no assumption that this is the case. So in theory, it could be also miners on both Bitcoin and Ethereum, but the protocol does not make any assumptions about that. And one thing again to mention that the committee is currently restricted. So you cannot currently become one of these signatories. Now, the verification of the correctness of the locks happens using a chain relay. So you don't really have a trusted third party here, but instead you have a smart contract. So it's basically enforced by the consensus of the target blockchain, and it's a programmatic check. So you only assume that the target blockchain works correctly. You don't require the miners of Ethereum to execute any specific steps. They just check that, you know, the execution does not fail, and that's it. And they don't really care about what your smart contract actually does. Some interesting maybe technical details about TBTC is that TBTC uses threshold DCDSA to generate a deposit address for each user. So at each time a user wants to mint TBTC, a committee is selected at random. I'm not sure how big the size of this committee is. I think it's 7 or 11. I'm not sure. And then you basically need the majority of signatures in this committee to lock and then also spend these assets. A problem with threshold DCDSA here is that currently, at least the current implementation, to the best of my knowledge, does not support fault attribution. So this means if the committee misbehaves, or the majority of the committee misbehaves, you also have to slash the honest participants because you don't know exactly who misbehaved and sign the transaction that steals users' assets. There is a new paper by Gennaro and Goldfeller at CCS this year that proposes the mitigation, although there's been another paper released recently that kind of introduces another attack. So it's an interesting scheme, but there's a back and forth about its security. And then finally, Xclaim, and also another paper that kind of goes in a similar direction to Dutch Ethereum, have a similar approach, but are more versatile and more essentially generic. The difference being, so Xclaim, or similarities first, Xclaim uses a TTP, but this TTP is dynamic. So anybody can become a trusted third party, anybody can register as a vault. So essentially, TBTC, RenVM, and even WBTC custodian BitGo could become a vault by simply locking up collateral. And in Xclaim, we don't really care about how exactly the vaults are implemented, as long as we know what deposit address you have. So essentially, a vault could be run by a committee of signatories like TBTC does, and then the entire TBTC instance would be one vault or multiple vaults in Xclaim, and that works out of the box. Now, in Xclaim, we use collateral to secure user funds. So if vaults misbehave, they will be slashed and users will be reimbursed. And again, we have an external custodian, so there are no assumptions about any involvement in consensus on Bitcoin or Ethereum, let's say, or Polkadot. So interesting here is to mention that we have a single TTP basically for each request, for each protocol execution, but it's a dynamic and unrestricted set. So anybody can become a TTP. So essentially you can run your own vault and execute your own issue request, and you don't need anybody else. The verification happens using chain relays. So again, smart contracts that allow us to check that your assets are locked up correctly. So there is no trusted third party on the verification step. One interesting thing to mention here is that, as you can see, there is no abort step implemented in either of these protocols. And the reason is that we assume that when we move assets to Ethereum, when we lock up BTC, that the Ethereum blockchain will operate correctly. That's the assumption, because otherwise, why would we move Bitcoin to Ethereum if we would think that Ethereum breaks? Now, of course, you could implement an additional abort step if Ethereum were to fail. The question is, because Bitcoin has no smart contracts and no way to check that Ethereum, for example, has a failure, how do you enforce it? And then it becomes a shield and sword game where you can, of course, add verification using another blockchain, for example, Rootstock. And then, but then again, you have the problem, okay, but what if Rootstock fails as well? And then it just keeps on going like that. So that's why most of these protocols, don't have a dedicated abort phase, but assume that, well, if we made the lock, then we will actually be able to create these wrapped assets. Something that I did not mention, because this doesn't really work for Bitcoin, is our bidirectional chain relays. This is more interesting if you're bridging two chains that support smart contracts. For example, Ethereum and Ethereum Classic, or Ethereum and Polkadot. And in this case, you would use a smart contract on both sides. So you'd have a smart contract that holds assets locked on Ethereum, and a smart contract that holds assets locked on Ethereum Classic. And these smart contracts are then synchronized again using a chain relay. Yeah, if there is any questions, let me know. I think we're running over time a bit, so I'll cut it here. And I hope this was kind of interesting and provided a bit more insight into the different models to create wrapped assets nowadays and which models are actually implemented in practice.
Yeah, well, thank you very much, Alexei, for the wonderful talk.